Hello, hello, hello. This is Nicholas on this lovely Tuesday afternoon, wanting to finally get back to you guys and start doing some some math videos. Once again, I'm sorry for the maybe 3 months in the shadows. Hopefully I can make up for it with this joke here. The question is, of course, who was the roundest knight at King Arthur's table? And the answer is circumference. Anyways, I'm sorry I've been polygon for so long. I now would like to continue my series of videos I had from eons ago about the directional derivative as a linear transformation and using calculus and linear algebra, tying those two things together. And in this, I'd like to give some more concrete examples of how derivatives and integrals, these objects from calculus, are very much connected with matrices from linear algebra. So the big idea to hit home is that if you've got a linear transformation and it's in a finite dimensional vector space, so in other words, the matrix can't have an infinite amount of rows or columns, is in other words what that is saying. If we've got that linear transformation, we can represent it as a matrix. So for example, let's consider the set of all polynomials of degree 2 or less. So let's call it maybe P2 for the power on x being at most 2. And that's going to be the set ax squared plus bx plus c, such that a, b, and c are all reals. And so this is a three-dimensional vector space. And now what we usually use to study these are commutative diagrams. So we consider an element of P2 and we see, well, what happens when I take the derivative of some element in P2? Well, I get something else that's also in P2. And then what we do is we make a sort of association between some member of P2 and the set R3, in other words, three-dimensional space. And then we see how that object in 3D, in R3, maps to another object in R3 via some matrix D, which we call the derivative matrix. You know, it's the matrix that represents taking the derivative of an object in P2. And then, of course, P2 via taking the derivative here, it maps to R3 via taking the derivative matrix here. So what does this look like more concretely? Let's consider an arbitrary element of P2, so that's ax squared plus bx plus c. And what happens to that when we take the derivative? Well, obviously we just get 2ax plus b. Now, the more unusual part is we make an association between this arbitrary element of P2 and the vector space R3. And so the most natural kind of association is to view the powers of x as the standard basis vectors. So in other words, we match this with the vector A, B, C. And then if we were to think about matching this 2ax plus b with a vector in R3, the most natural choice, given our association here, is 0 2a b, right? Because there's no x squared coefficient, so there's a 0 there. And now the question is, what is the matrix D that maps this vector onto that vector? And the matrix that does that, we would kind of most naturally call the derivative matrix. It's the linear transformation that represents taking the derivative of ax squared plus bx plus c. And D is not that hard to find in this particular example. It would turn out to be, well, the first row would need to be all zeros because we have a 0 here. And then the next row, we'd need a 2 contribution from the A, and then zeros for the rest. And then For this last, we need a 0, a 1, and a 0 because we need one contribution from the b and nothing from the rest. And so this is, and there's other ways to go about finding d, but that is what the derivative matrix looks like for this sort of derivative operator in R3. And this kind of makes sense because we have this 2 matching up here with this, this 2 matching up with that 2, corresponding to a power of 1, since it's in the second row, and then this b here corresponding to a power of, x to the 0 because it's on the third row. Okay, so now let's consider maybe taking the integral of some sorts. Well, it's a little more problematic in this case because when we took the derivative of something in P2, we got out something in P2. But if we take the integral of something arbitrary in P2, we don't get something that's in P2. So let's maybe consider just taking a definite integral over certain bounds. Let's say P2, and we take the integral of some arbitrary element in it, which I'll just draw with kind of a box, dx, kind of sloppily. And we take the definite integral of something in P2 from 0 to 1. Well, of course, that just maps to a number, a real number, which is in R. And then once again, we match something in P2 with the vector space R3. And then in this case, the commutative diagram would not be a square, it would actually be a triangle because the integral is a little problematic here because it's not something in P2 already. So we just would map from R3 to R like that. So in this particular case, we have ax squared plus bx plus c. And we take the definite integral of that from 0 to 1, and we get a over 3 plus b over 2 plus c. And you can check that for yourself if you'd like. Now, again, we think of associating something in P2 with the space R3. And again, the most natural association is to associate the quadratic with the vector ABC. So again, the powers of x representing the standard basis vectors in R3. And then we need to see how we can map this vector onto this constant here, right? And so that involves doing some sort of dot product with another matrix, right? We have a 3 by 1 matrix here. We need a 1 by 3 matrix so that when we do the dot product of two vectors, because vectors are just matrices, we would get a constant. We'd get something in R, R1. And that matrix is relatively obvious as well, right? If it's the matrix 1/3, 1/2, 1. So this represents dotting the vector ABC with the vector 1/3, 1/2, 1. And of course, that dot product gives us that number in R. And so this matrix we would call I, and that sort of represents the definite integral as a linear transformation in this particular vector space. But it's kind of neat to see that with very natural associations, there is, of course, in every case, a concrete matrix represented by taking the integral. So now let's consider maybe something a bit more practical, a different vector space. Let's consider vector space V, which is defined as the span of e to the x sine x and e to the x cosine x. And so remember that the span is just any linear combinations of the elements of the vector space. So that would be something like a e to the x sine x plus b e to the x cosine x. Okay, so we consider V. Let's look at derivatives and integrals with V. we take the derivative of something in V, and we get out, of course, something in V. And then we associate. Now, I'll also realize that this is a two-dimensional vector space, right? Because it's just two elements being considered in the span. So they can at most span out the entire plane of R2, but certainly nothing more than that. Anyway, so now we would kind of want to associate V with a vector in R2 and then see how that vector in R2 gets mapped to another vector in R2 via the derivative matrix, if you will, D. And then that completes the diagram. So we have A e to the x sine x plus B e to the x cosine x. And this is the arbitrary element of V, right? That's what it means for something to be in the span of two elements. And then now we take the derivative of that, and that turns out to be A minus B e to the x sine x plus A plus B e to the x cosine x. And now the most natural association between the arbitrary element of V and something in R2 is to essentially make e to the x sine x play the role of I hat 1, 0, and e to the x cosine x play the role of j hat 0, 1. So we associate this with the vector AB. And this is really kind of a very powerful technique because you can have something really, really yucky here, but just kind of have it be the representative of the standard basis vector in your vector space, and it kind of goes away. Okay, and then now this is, of course, associated with, naturally, the vector A minus B, A plus B, given our association on the left. And so now we just need to find the derivative matrix D that maps from this vector to that vector. And this matrix is straightforward enough. It would be 1 minus 1, 1, 1, right? Based on these coefficients right here. And so now that is kind of a way to represent the derivative in this vector space. But now let's maybe consider the integral, right? Now, by the fundamental theorem of calculus, right, the derivative and the integral are kind of inverses of one another. So naturally, D inverse is sort of this integral matrix I, which, following the formula for inverting a standard 2 by 2 matrix, is 1 over the determinant of the matrix, which is 1 over 2 in this case, times, and then we flip along the other diagonal. Oops, 1, negative 1, right? That's just a standard formula from like pre-calc or something like that. And that is sort of our integral matrix I, which we can actually use to, let's say we wanted to compute the integral of e to the x sine x dx. So what we can do is sort of associate this with D inverse, or I, times the matrix 1, 0. And it's times 1, 0 because, like I said before, e to the x sine x is playing the role of I hat here, and e to the x cosine x is playing the role of j hat there. And we just have e to the x sine x, so that's I hat 1, 0. So we have a half times 1, 1 minus 1, 1 times I hat 1, 0, which is a half times 1 minus 1. It's just some matrix multiplication. And now we sort of bring that back in terms of, our normal functions of e to the x and sine x and cosine x. And what does this represent? It represents a half e to the x sine x minus e to the x cosine x. And voila, we've just, using linear algebra, without having to do integration by parts or anything like that, we found the integral of e to the x sine x, in my opinion, in the simplest way possible. And with that,